Okay, so now we're going to look at neural networks, or more specifically, the multilayer perceptron, and I'm going to talk a bit about the idea behind this classifier and how it works with linear discrimination, so the original perceptron and the idea of using one neuron. And then we're going to see the multilayer perceptron and how it can do nonlinear discrimination by transforming the input values along the network. And then we're going to see backpropagation, the algorithm for training multilayer perceptron, and regularization in multilayer perceptron. So the idea here is inspired in neurology, in the neuron. And a neuron has more or less this shape. It has this nucleus, a long axon, a long wire, so to speak. It can have several, but long ones that end in these synapses. So at the end, the neuron can release neurotransmitters and pass on the signal to another cell. And on the other side, it has these dendrites that receive the input, so to speak. So basically, what the neuron does is a sort of a switch. If the stimulus it receives on the dendrite is not sufficient, then nothing will happen. But if the stimulus is large enough, then the neuron will fire and it will depolarize the membrane, and this signal will spread across the axon up to the end. So basically, the neuron gives a nonlinear response. It's a no or nothing response. If the stimulus is too low, it's silent, but when the stimulus is high enough, it will fire a large impulse. And this was the inspiration for the original perceptron, which basically has this weighted sum of the inputs. Each input value is weighted by a specific coefficient. They are all added together, and now we have a threshold here that determines whether or not the neuron fires. So if the total value here is above the threshold, the neuron fires 1. If it's not, then the output value will be 0. So basically, we have a step function here that determines whether or not the neuron fires. So this was the idea of the original perceptron. We have a sum of the input values plus a bias value here that can shift the function somewhere, and if the result is greater than 0, the neuron will fire a value of 1. If it's 0 or less, the neuron is silent. To train the perceptron, we will present it with different examples, and if there is a mistake, if the target value we have is different from the output of our neuron, then we update the weight of the neuron by a small amount here. So basically, this is the update rule. We update by a small amount, and the amount is some fraction of the difference between the desired output and the actual output of the neuron multiplied by each of the input values that came through that weight. So, for example, for this input value goes through weight 1, we use that input value here as a multiplier of the adjustment. So the larger the input value, the larger the adjustment, and only in those cases where the neuron makes a mistake. If the neuron does not make a mistake, then this difference is 0 and nothing happens. Okay? So this was the original idea of the perceptron. And basically, it gives us a classifier that outputs 0 or 1. We can train it with a set of examples. This seemed to be very promising because it was a generic way of learning anything, until they found out there was a big limitation here. Because if you use only one neuron, then it's actually a linear classifier, because you have a linear combination of these, and then you decide based on the linear combination. So if you want to make things a bit more complex, we need to find a way to propagate the error backwards, as we're going to see in backpropagation. So we actually need to have a function that is not linear in the output, but also not like this with a step, because the derivative of this function is discontinuous, and so we cannot compute how to propagate the error in this case. So actually, usually the neurons we'll see, the classical ones, use something like a sigmoid function, for example, and in this case we have something that is very similar to logistic regression. So basically you can imagine that one neuron with a sigmoid activation function works like a logistic regression classifier. It does a linear discrimination using that curved logistic function here. So strictly speaking, the term perceptron was used first for that original network of a single layer of neurons, each one trained with that rule, with the stepwise activation, and each one trained with this rule here. The thing is that with a single layer, each neuron can only do a linear discrimination between the examples, and so this was a limitation of the original idea. However, we also use the term perceptor, specifically in multilayer perceptron, when we're talking about a neural network that is fully connected and has several layers. So we're not going to worry much about the name. This is just an idea that this name has a historical meaning, but then was adapted for more modern applications. So let's see what one neuron can do. One neuron with a sigmoid activation function works pretty much like logistic regression. So we can classify linearly separable sets. This is a classical example. I'm representing here the OR function. So false and false is false, false and true, true and true, or true and false are all true. So these are two classes with the combinations of zeros and ones here. To train the neuron, we're going to minimize the quadratic error between the output of the neuron and the class that we want. So each class here is 0 or 1, 0 the blue, 1 the red. We can measure the difference between this 0 or 1 in the class and the output of the neuron, which can go from 0 to 1. It's that sigmoid function. And now we can present each example and adjust the weight of the neuron. So the idea here is that we have the neuron works like this. It has weights for the different inputs, and then we add everything, only that the function now is this sigmoid, this logistic function that we have. So in order to train this, we must assign to the weights of the neuron how much we have to change them based on the error of the neuron at the output. But since all of these functions can have continuous derivatives, we can propagate backwards or propagate the error through all these functions by using this chain rule. So basically what we want to do is we want to go down the derivative of the error function as a function of the weight. We need to consider the error here, so the difference between the output and the target function. But then we need to propagate this, go back here through the logistic function, and then through all the sum of the different input values multiplied by the weight. So we can do this like this. This is a chain rule. So basically the derivative of the error with respect to each of the weights we are adjusting is the product of all these derivatives. The derivative of the error with respect to the output of the neuron, and this is simply, we have the quadratic error function, the output of the neuron, and the desired value for that example, and we compute the derivative. We have this expression. And then we can compute the derivative of the output of the neuron with respect to what goes into the logistic function. So basically this is the logistic function, this is the derivative. And then we compute the derivative of the weighted sum of the input with respect to each of the weights on that neuron. So since the weighted sum would be this bias value here, plus the sum of this each weight multiplied by the input, when we compute the derivative with respect to one weight, this is simply the input value that came through that weight. So now we multiply everything, we have this update rule. So basically we are going one small step in the direction of decreasing of the derivative of the error with respect to the coefficients there, the weight. This small step will be given by a small value that we multiply here, and then we have here the result of the chain rule. So basically this is the update rule for a single neuron. Now we can apply this here. So basically what we have here is the difference between the output of the neuron and the target function multiplied by the value of the output of the neuron multiplied by 1 minus this. This is because of the logistic function that we're using. If we were using another function, this part could be different because it would be the derivative of that function, and then multiplied by the x, the feature value that comes through this weight. And this tells us how much we have to change the weight to adjust the output of the neuron. And now we're going to do this either by online learning, so one step of the type, or at a time. This is called stochastic gradient descent because we are descending the gradient. We are going in the negative direction of the derivative of the error, so we are going down that surface. And it's stochastic because we are picking examples at random. So if we present one example, we can go one way, and then we present another, we can go another way, and so on. So this would be with online learning. We give the examples to the network, and for each example we adjust the weight of the neuron, and then we give another example, so forth. Another way of doing this would be by batch training, where we present each example, we keep adding the difference, the change in the weight that we had to apply, but we don't apply them yet. We do that for all the examples, all in the same point, and then we jump by changing the weight coefficient by all those updates. But either way, what we're doing is we are presenting examples at random. We are computing how to change the weight of the neuron to improve, to reduce the error, and then eventually we update, and we keep doing this. So this is how we can train in this example. These are several runs. So these are the training errors. These are different epochs. One epoch is one pass through all the data, and in one epoch the points come in a random order. So for the first epoch we presented these 4 points in some order, then the second epoch we presented the 4 points in a different order, and each time we present the points to the network we do a slight adjustment on the weight. So the training error starts to reduce, and eventually everything stabilizes. And here we have what the neuron is telling us. The neuron puts the discriminant here, and it's separating these blue points from the red points. So this works. One neuron works for classifying something that is linearly separable. However, if we have something that is not linearly separable, and this is the classical example that disappointed a lot of people in the beginning of studying neural networks, which was to show that one neuron cannot work in these cases. And this is the exclusive OR function. So false and false is false, false and true and false are true, but true with true is false again. And this is not linearly separable. There is no straight line you can put there that can separate blue from red. So if we try to train one neuron like this, we always have this error here. So basically this is the quadratic error. It's failing 50% of the time, or an average error of 0.5. 0.5 squared is this 0.25 that we have here, and the error never reduces. And we have something here that is, well, it doesn't work because it puts the 2 red points on this side, but this blue point is also on the red side, and only that one is correctly classified. So there is no way the network can correctly classify this, and the error does not reduce. So this is where the multilayer perceptron comes in. One neuron cannot classify something that is not linearly separable. It will always commit some error, but we can add neurons in a network in different layers. So this would be what we're going to use, the network we're going to use to solve the exclusive OR problem. These H1 and H2 are the hidden neurons. we don't see their output outside the network. They are hidden by the output neuron inside the network. But these neurons receive the input values, the feature 1 and feature 2. These values 1 here will serve to represent that additional bias value that can shift the sigmoid function more to the left or right. So basically, we have a weight here that simply works to reduce or increase the threshold where the neuron fires. And then we have the output neuron that will receive as input not the actual input values, but the outputs of the previous layer. So this is a multi-layer perceptron. It is fully connected in the sense that each layer is connected to all each neuron in each layer is connected to all the neurons in the following layer. It feed forward. All the connections go from one layer to the next. They don't go back. They don't have loops or something like that. In this case, we have these input values here, one hidden layer of neurons, two neurons in the hidden layer, and one neuron in the output layer. So this is a multi-layer perceptron with three neurons, two in a hidden layer, one in the output layer. And all these, we're going to assume they have a sigmoidal activation function. So now, the trick of training a multi-layer perceptron is similar to what we did with one single neuron. We have to assign the blame, so to speak, for the error in the output of the neuron all the way back to each of the weights. So for the output neuron, this is the same as we saw with a single neuron. The only thing is that the input in this case is not the x value, but the output of the previous layer. So basically, we need the chain rule to compute all the derivatives, the derivative of the error with respect to the output of the function, so this part here in the quadratic error, then the derivative of the output of the logistic function with respect to the weighted sum of the inputs, and it's this part here, and then we need to compute the derivative of that with respect to the input. So what we can do is we can compute all these parts of the derivative which is characteristic to that particular neuron, let's call it the delta, and then we can compute this for each of the neurons starting from the output and then going back. Now when we go to the hidden layer, this is where things start getting a bit more complicated, because now we have to continue this, computing the derivative and going back to the previous layer. So the idea is the same. We are going to continue to compute the derivative from the error backwards to all the weights that we want to update. But now for computing the adjustment, the update for the weights in a hidden neuron, we need to consider all the neurons that are ahead. So the idea here is that if we want to update a weight in this neuron, we need to consider that this neuron will contribute to the error of these two neurons in the next layer. So if we have several neurons on the different layers, we need to bring back the computation of all these derivatives from each of the neurons that is in front of this one. So this is this sum here. We are going to compute for each neuron that is in front. We are going to sum all of that, and then we're going to carry on to multiplying the derivatives of the logistic function and of each of the weights in that weighted sum. So this is the idea. This would be, if we write the whole expression in completely, it would be a very large expression, but we can take advantage of these parts here that are for each neuron they have one value. So we can call that a delta. We can compute the delta for each neuron, and then we use those to do the update. So basically the difference is that for the output neuron we do this one. For the hidden layer neurons we have to do this for each neuron that is in front, add all the contributions to compute the delta for that. So this is how the backpropagation algorithm works. We present an example to the network and we activate all the neurons by propagating forward. So the neurons on the first layer, we activate them. We use the output of those as input for the second layer, and so forth. So we light up all the network with this example. Now that we have all these values and we can compute the error, we can start propagating backwards. So we're going to compute the delta, these products of the derivatives for the last neuron in the last layer, and then we're going to do that for the hidden layer all the way back to the beginning. And then we can use those deltas to adjust the weights of the layers. So this is what is the backpropagation algorithm, and this is what allows us to train a multi-layer perceptron, a neural network with several layers. So let's see the exclusive OR problem with this network, the three neurons, two on the hidden layers, one on the output layer. And what we do here is, again, we present these points, this data set, in a random order in each epoch, and we adjust the weight of the network for each of the examples slightly. You can see that this takes some time. So in the first nearly 10,000 epochs, nothing seems to happen, but then in some runs before that, in some runs later, but eventually the network starts learning. This is a stochastic process because we are showing things at random, and also we initialize the weights of the network at random, so it doesn't go the same way every time. But eventually the network starts to learn, and if we let it run long enough, the error decreases down to zero. And this is what the final result is. So if we present data points in this plane, this network of three neurons can separate these two regions for the red class and this strip here for the blue class, even though the last neuron can only separate linearly separable classes. So what's going on here? We can look at what's happening from the perspective of the final neuron. So the last neuron, the output neuron, is not receiving the actual features, but it's receiving the output of the two neurons in the hidden layer. So this would be the output of one of the neurons in the hidden layer, and this the output of the other neuron in the hidden layer. As you can see, neither one of these alone can properly separate these points, because this one here, if we project all the points here, we have red, then two blues, and then red here, and it cannot separate them. And the same thing goes for the other neuron in the hidden layer. It can also not separate the points properly. But when they respond in this way, the output neuron is actually seeing a transformation of the input into this shape that now is linearly separable. The output neuron can now draw a line here and separate the two classes. So basically, remember what you did by hand with those feature transformations, those nonlinear transformations with the logistic regression to allow us to do something that was nonlinear. The network is doing this on the hidden layer. The reason why this is nonlinear is because although we start with a linear combination of all the inputs and the weights, then we pass through that sigmoidal function which is not linear. And the network does a nonlinear transformation of the point. Each of the inputs of the hidden neurons can do its own nonlinear transformation. Alone, they cannot solve the problem, but now they can present to the output neuron something that is in a different shape, and the output neuron can classify it. The reason why this takes longer to learn is that the output neuron can only learn the proper classification after the hidden layer has learned how to adjust things properly. So this takes longer to learn than if you use one single neuron. And if you add more layers, like in deep learning, which you'll see at the end of the semester, then things become even worse. But the idea here is that eventually the hidden layer can transform the data in an adequate way for the output neuron to classify it properly. So this can be used in many different ways. This is just to give you another example. This is an old idea, the auto-associator. Instead of having one network that produces a classification with one output neuron, for example, we have a network that has the same number of outputs as it has of inputs. So basically what we're doing here is we don't have labeled data, we just put something in and we want the same thing coming out. And the interesting thing happens here inside. So this is an example, the autoencoder. Let's suppose that the input and the output has to be 1, 1, and everything else at 0. So it can be either the first input set at 1 and the other at 0, or the second at 1 and the other at 0, and so forth. So we have 8 possible inputs in this way. And for each of those, we will require that the output is the same. So if we put a value of 1 here and 0 here, we want a 1 to appear in that neuron and 0s in all of these. And if we train this enough, we can see the error coming down, so eventually our network can output the same thing as the input, which is not very interesting because we are not doing anything new. But the interesting part here is that the hidden layer only has 3 neurons. So even though we have 8 here and 8 here, there are only 3 here. And the network needs to do this thing, copying this input to the output, using only these 3 neurons. And what happens is that in these 3 neurons we will have all the 8 combinations of zeros and ones. So basically we are creating a binary encoding of these inputs. It's not necessarily in the same order, but the network found all those combinations to be able to copy the input to the output. So this is something that can also be used up to recent years, like about 2015 or something like that. It was something that was used in deep learning to help train deep networks. But basically, what I want you to retain from these examples is the idea that in a neural network, the hidden layers are transforming the data in a different representation that then will be used by the last layer to do the classification. So what we did by hand with logistic regression, by adding in those additional features, the network is doing automatically in the hidden layer. So in practice, we want to start with random values for the weights that are close to 0. The reason for this is that we are adjusting the weight by computing those derivatives, and if we are very far from 0, the derivative of the logistic function is 0, and then there is practically no update. So training will be very slow. So it's best if we start with small weights, positive and negative, at random for the whole network. It's also important to, in this case in neural networks, to standardize or normalize our data. We don't want very large values coming into the network because that will also will saturate the logistic function. Another thing, since we are starting with random values and then presenting examples in random order, things will not always go the same way. So run several times the network and look at what's happening. So standardization or normalization is important. We don't want to saturate the network with very large inputs, and also because we are using the same learning rate for all dimensions. And if you have some neurons where very large values are passing through and others where very small values are passing through, the update will be different and it will take longer for the network to learn. So you should have everything approximately at the same scale. The logistic function outputs between 0 and 1, so this can be the values we use for the class. And for multiple classes, we can simply use multiple output neurons. So each one will tell whether or not the point belongs to that class. For stochastic gradient descent, we are presenting examples in a random order, but we pass all the training sets, all the training examples in some random order before passing them through again. So basically each epoch is one pass with all the examples, but we shuffle the order in which we pass them. And then we evaluate the error. We can use this same quadratic error if we want to do cross-validation or something like that. We can do regularization also in neural networks in a simple way. Remember that regularization is something that tries to reduce overfitting by changing the way we are training the model. So we're finding the hypothesis. One simple way of doing regularization in a neural network is to stop early. So here you can see the blue ones are the cross-validation error. You can see that as we run several times, after a few epochs here, maybe around 30, the cross-validation error tends to start increasing. So even though the training error keeps decreasing, the network is overfitting the data. So one way of avoiding this overfitting is we stop instead of letting it run all the way, we stop around here and we minimize the overfitting this way. Another example of regularization in neural networks is to use this weight decay. So every time we update the network, we also reduce a bit the magnitude of the weight. We use a small value for that, but we keep bringing the weights down to 0. So if these weights are not important for classifying, for reducing the error of the network, they will eventually come down to 0 and will be turned off. If they are important, they will keep increasing, so it keeps growing, and the network will keep them alive. So there are several different ways of regularization, but the idea here is also to illustrate this difference between model selection and regularization. So regularization is not only when we add a penalty to the coefficients, for example, as we saw in the polynomial regression, but it is any method that changes the training of our classifier, for example, no matter how we change it, either by stopping early or by decreasing the weight or something like that. So to sum up, we saw what was the perceptron, classically the one with the stepwise function. Also, more modernly, we can call multilayer perceptron this neural network of fully connected layers and feeding forward. We saw this idea of stochastic gradient descent, stochastic because we are presenting the examples at random, and the gradient descent because we are going down the derivative of the error. So we're going to try to find the minimum of the error. We also saw backpropagation. So there are lots of equations here, but the idea is basically that we are using the derivatives of all those functions that we are composing, and we are multiplying the derivatives to assign what blame, so to speak, each weight has for the error and how to change that weight. And saw a few ways of regularizing the training of neural networks. So if you want to look at backpropagation, this book by Mitchell is a bit old, but has backpropagation very well explained there. One thing to take care is that sometimes, for example, in Alpidin, the output neuron is assumed to be linear. This changes the derivative there in the backpropagation, so you may find slightly different expressions there if the output is linear or if the output is logistic. So take note of that depending on where you find the explanation. Okay. And that's it for today. I don't know if you have any questions.